Incorporating tactile feedback into deep reinforcement learning can significantly enhance robot performance in contact-rich scenarios such as object occlusion, delicate manipulation, and high-speed sliding. However, exciting tactile hardware varies widely in types, including resistive, capacitive, optical, piezoelectric, and vision-based principles. Such complex principles and diverse models of tactile signals in the real world lead to a lack of universal simulation modeling paradigm. In addition, mainstream simulated tactile sensors have drawbacks. For example, finite element method-based sensors are computationally heavy, while penetration depth-based methods also face huge computational pressure in large-scale contact-rich tasks due to massive contact detection. Most critically, there remains a substantial domain gap between simulated tactile platforms and real-world tactile sensors. Thus, we first design a uniform and high-speed tactile simulation model, enabling efficient, large-scale DRL training on GPUs. Now we introduce our ConTact framework. First, we generate paired data. We record object trajectories in both simulation and the real world, then match the corresponding sequences to form training tactile pairs. We then use contrastive learning to align the features from these pairs. A contrastive loss brings the sim and real representations together. A reconstruction loss then predicts frame-to-frame differences, teaching the model to capture contact dynamics, not just static images. This is handled by our spatiotemporal encoder. A spatial module processes each frame using a CNN enhanced with a CBAM attention block and residual connection. A temporal module, which imply a feature difference strategy and 1D convolution, analyzes the sequence over time. We train the policy using an asymmetric actor-critic framework. The policy is trained entirely in simulation. For real-world deployment, we achieve zero-shot transfer by simply swapping the simulation encoder with the pre-trained real-world one. This is possible because our framework has already aligned the features across both domains. We demonstrate our method on two tactile-only tasks, single and composite object tracking, SOT and COT. The goal is to balance an object on a tray while tracking a dynamic trajectory. The COT task is more complex, requiring the robot to maintain the structural integrity of a multi-part toy car. We train our policies to track 4 different trajectories and achieve zero-shot transfer to the real world. In the COT task, we shift the car's body forward/backward relative to its wheels at initialization. Circular trajectory. We also apply light taps with a hammer to the car's body to test its robustness under perturbation. In the SOT task, the policy successfully complete all 4 trajectories with spheres of varying diameters and materials. In a particularly challenging test, the policy seamlessly adapts to real-time object switching during trajectory, completing this task for over 8 consecutive trials without failure. During a lemniscate trajectory, we apply light taps with a hammer to the ball. The policy successfully recovers and stabilizes the object. The policy success on the ascending helical trajectory, each featuring a different ball initiated from a distinct off-center position. Thanks for watching. Please refer to the paper for more details.